Hi everyone, my name is Xiongzhi Chen. I am an assistant professor from the Department of Mathematics and Statistics at Washington State University. In this short presentation, I will talk about a new method on estimating the proportion of false null hypotheses via Lebesgue-Stieltjes integral equations. Here is the outline of the presentation. We will go over the background on the proportion, quickly review some existing estimators of the proportion, and present the new method and its performance, and then summarize the results. The proportion of false null hypotheses is also referred to as the signal proportion or alternative proportion. It plays important roles in statistical modeling and multiple hypothesis testing. For example, it appears in the upper bounds on the false discovery rate and false non-discovery rate of a multiple testing procedure. It is a component of the two-component mixture model, its extensions, and their induced statistics. It forms the optimal discovery procedure. However, the proportion is unknown and needs to be estimated. The estimation problem can be formulated as follows. We have random variables zi, I from 1 to m, each with mean or median mu I. The zi's are usually statistics. The ith hypothesis tests if mu I belongs to theta 0, the null set that's pre-specified, or not. The indices of signals contain I for which mu I does not belong to theta 0. And the signal proportion, denoted by pi sub 1m, is defined by m1 over m, where m1 is the number of signals and m is the number of hypotheses to test. We will consider three types of nulls. Simple null, meaning that theta 0 is a singleton theta 0 that's pre-specified. Bounded null, meaning that theta 0 is a finite open interval where a and b are pre-specified. One-sided null, meaning that theta 0 is the interval from -infinity to b. These three types of nulls generate the commonly used nulls. Our target is to construct an estimator hat phi sub m depending on a tuning parameter t and the data z, to consistently estimate the proportion in the following sense. There are some existing estimators of the proportion. For the case of simple null, we have Story's estimator, deconvolving estimators, the MR estimator, and Jeans estimator. For the case of a bounded null, we have Jeans estimator, but only applicable to symmetric bounded null. For one-sided null, we don't have any estimator yet, due to the non-uniformity of p-values under composite nulls or the failure of deconvolving methods. The consistency of these estimators requires one or two or all of the following three. The CDFs of ZIs being absolutely continuous, the ZIs coming from mixture models with the Gaussian component, the ZIs being identically distributed under the alternative hypothesis. To remove these restrictions, we will introduce the new method via Lebesgue-Stieltjes integral equations. Denote by f sub mu I the CDF of ZI, such that f sub mu I is a member of f of CDFs that are indexed by mu, and assume that each f sub mu is uniquely determined by mu. The new method starts by constructing a bivariate function psi, such that as t tends to infinity, psi of t mu converges to 1 for each mu belonging to the null set, whereas of t mu converges to 0 for each mu belonging to the alternative set, which is the complement of the null set, and then constructing a bivariate function k that does not depend on any mu belonging to the alternative set and that satisfies the following Lebesgue-Stieltjes integral equation. The equation connects psi with k and f sub mu, and then setting the estimator of the proportion to be the following. Note that the estimator hat phi sub m is an average of quantities involving k, the tuning parameter, and data. The main difficulties in implementing the method are given below. They concern the existence of psi that satisfies the limiting conditions, the existence of k that satisfies the Lebesgue-Stieltjes integral equation, and the control of the stochastic oscillation of the new estimator. Nonetheless, here is the summary of theoretical results for the new estimator. When zi's are independent, the new estimator is uniformly consistent, respectively, for all three types of nulls, if in addition zi's have CDFs that belong to a type 1 location shifter family, such as a Gaussian or Laplace family, or a continuous natural exponential family with separable moments, such as a gamma family. It is also uniformly consistent for the case of point null if in addition zi's have CDFs that belong to a natural exponential family with support n, such as a Poisson or negative binomial family. Now we present some simulation results. This plot shows the performance of the new estimator when it is applied to independent negative binomial random variables under the setting of a point null. On the x-axis, we show the number of hypotheses to test. On the y-axis, we show the excess of an estimator. The more concentrated the excess is around 0, the better the associated estimator is. We consider 4 sparsity settings that are indicated by the proportion values that are given in the strips. And for each m, the box plots of the excess of each of the 3 estimators are shown as follows. The left box plot is for Jing's estimator, the middle one for the MR estimator, and the right one for the new estimator. The red diamond is the standard deviation of the corresponding estimator. We can see that the new estimator in general outperforms Jing's estimator and the MR estimator. This figure shows the performance of the new estimator when it is applied to weakly dependent Gaussian random variables under the 3 types of nulls. The x-axis and y-axis settings are the same as the previous plot. We consider 2 sparsity settings and 3 settings of weak dependence. Note that for bounded null, the MR estimator is undefined and is hence not shown. For each m, the box plots of the excess of the 2 estimators are shown as follows. The left box plot is for the MR estimator and the right box plot is for the new estimator. We can see that the new estimator in general outperforms the MR estimator in terms of accuracy and stability. In summary, solutions to Lebesgue-Stieltjes integral equations can serve as universal constructions for estimators of the signal proportion and its functionals. Under independence, the proposed estimators are uniformly consistent, Some of them are consistent even under weak dependence, and some of them are quite robust. The consistency and speed of convergence for each such estimator are largely determined by the moduli of the characteristic functions of the CDFs of the random variables. Here are the acknowledgements and key references. The contents of this presentation are drawn from these two publications. And the rest two slides contain additional references. If you have questions, please contact me at the email address shown here. Thank you for your attention.